My name is James Kelly, and this is my overview of Lab 1, Motion and Newton's Second Law. Introduction. The purpose of this lab is to create an observed and computational model of the motion of a ball in a single direction with no additional forces affecting it. The observed model is created with a video of a ball moving, put through a software which will track the change in position of the ball over time. The computational model is based on a program that iteratively changes position over time based on a constant velocity. The primary physics principles involved in this experiment are position, velocity, net force, motion, and Newton's second law. The main results of this experiment are that both models exhibited behavior consistent with modern understanding of motion and Newton's second law. Now I'm going to go over and define the main physics principles in more depth. Position is a vector quantity which describes where an object is currently in space. Velocity is another vector quantity, this one describing the change in position over change in time. Net force is a vector or magnitude that describes how velocity changes over time, accounting for the mass of the object. Motion is a characterization of how position changes, and Newton's second law describes how net force affects the change in velocity of an object. Newton's second law is characterized by the equation net force equals mass times change in velocity over change in time. This equation can be rearranged into several different derivations, such as the position or velocity update formula. The position update formula is R final equals R initial plus V average times delta t. And delta t in this case is change in time, V average is average velocity, and R is representative of position. The velocity update formula is V final equals V initial plus F net over m times delta t. In this case, m is equivalent to the mass of the object, and F net is another way to say net force. The software used to obtain the observed results analyzed the position of the ball in the video over time as the ball moved leftward in the negative x direction. The software then recorded the position at different frames based on time elapsed, the scale established for the meter stick in the video background, and a set of axes established at the ball's starting position, which is considered to be 0, 0. It then created a graph based on the observations, which shows the effect on position over time. This model was chosen because it represents the specific observed results of the experiment. The ball is initially at rest, which is represented by the lack of change in position for the first few movements of the tracking model. The computational model was created using a Python program. The iterations it uses are calculated with the velocity update formula and then position update formula, applied using a uniform change in time. The program then graphs a change in position and a 3D model of the predicted motion. The program assumes there are no net forces acting on the velocity of the ball, making the overall change in velocity equal to 0. The computational model is a perfect prediction using Newton's second law and is considered the expected results of this experiment, which is why it is used. The program also accounts for the brief period in which the ball was stationary at the beginning of the video. The initial conditions is a ball at rest with a position of 0, 0 and an initial velocity of 0, 0. The system in this experiment is the ball, and the surroundings are the universe around the ball. Throughout the experiment, it was assumed that there were no net forces acting on the system. The only force being applied was the initial rolling of the ball. This assumption is made in order to create the computational model in a way that we can correlate it with the observed data. This means it is also assumed that there is a constant velocity based on Newton's second law and the velocity update formula. Discussion. This is the combined data between the observed and computational model. In this graph, R1 represents the observed data, and R2 represents the data from the computational prediction, both of these being expressed in position, in the x direction. Both graphs show similarity in final versus initial position, and both graphs show no change in a velocity. This indicates that the motion of the ball is consistent with Newton's second law as applied in the computational model, with no net forces affecting the motion of the object. There is only a slight difference in the final position, which will be investigated later as a result of a source of error. There's another question that could be asked here, which is what if the axes became flipped? Well, if the axes did become flipped, it would not actually change the root observed effects, but merely switches the position to be positive instead of negative as it currently is. Further, because the position would be getting larger in the x direction, the velocity would also be positive. Overall, the main observations of this lab, i.e. the consistent changes in position over time, would not change regardless of orientation of the axes. So, what does this all mean? The results indicate that Newton's second law of motion was observed and supported during this experiment. Because the observed model was so similar to the computational prediction, it means there was a net force of 0 acting on the ball during its motion. The lack of change in slope on the position graph is also indicative of a constant velocity, which further corroborates the assertion that there were no net forces acting on the ball during its motion. It is impossible to tell exactly how many forces are added together to reach this net zero force. because the surroundings are the entire universe around the ball. One source of error, however, comes from the assumption that there are no net forces acting on the ball once it begins its motion. Because the ball is rolling on a table, there's undoubtedly a friction force that is affecting the velocity of the ball and thus slowing it down. Friction is a force characterized by contact with another object causing a decrease in velocity. This source of error is seen in the observed data versus computational model comparison, in that the observed data does not travel quite as far as the computational prediction. Friction is most likely the cause of this difference.